Hello there and welcome to Mysteries Beneath Earth, where we pull back the curtain of the obvious to look at the machinery humming quietly in the dark. Tonight, we are going to ask a question that feels too large to hold, a question that changes the very ground you are standing on, or rather, the space you are floating in. We often look at the night sky as a window, a vast, open expanse stretching out into infinity. We think of ourselves as standing on a small rock, looking out into a limitless void. But what if that intuition is wrong? What if the sky isn't a window but a wall? What if the universe you know, with all its galaxies, its light, and its history, is not a vast open room, but the interior of something else? Tonight, we drift into one of the most unsettling and beautiful hypotheses in modern cosmology. The idea that our universe is actually living inside a black hole before your mind recoils at the thought. Because, after all, black holes are supposed to be monsters, destroyers, crushers of matter. I'd like you to take a slow breath. Let the anxiety of the words settle. Because in the language of physics, a black hole is not necessarily a monster. It is a geometry. It is a place where space flows in a direction that does not allow for return. And when you look at the mathematics of our own universe, the numbers begin to whisper a strange correspondence. The size of our observable universe, the amount of matter within it, and the way it expands, they match with eerie precision the conditions of a black hole that so settle in. Pull the blanket up a little higher. We are going to walk to the edge of the universe tonight, to the horizon that defines us, and ask what lies on the other side. To understand this, we have to first unlearn what we think a black hole is. In the popular imagination, created by movies and terrifying headlines, a black hole is a cosmic vacuum cleaner. We picture a dark whirlpool in space, sucking in stars and planets, tearing them apart in a violent frenzy. And while the environment outside a black hole is indeed chaotic, a place of superheated gas and X-rays screaming into the void, the interior is a different story. The interior is a mystery protected by the ultimate silence. The boundary of a black hole is called the event horizon. You've likely heard this term before. It is the point of no return. But think about what that phrase really means. No return doesn't mean destruction. It means disconnection. Once you cross that threshold, you can never send a message back to where you came from. The light from your flashlight, the radio waves from your transmitter, even the gravitational pull of your body. None of it can climb back out of the gravity well. To an observer on the outside, you simply vanish. You fade from view, frozen in time, and then you are gone. But for you, for the traveler falling in, you don't vanish. You don't necessarily even feel a bump. If the black hole is large enough, a supermassive giant billions of times the mass of our sun, the tidal forces at the horizon are gentle. You could drift across that boundary without even realizing you've left the known universe behind. You would look back and still see the stars you came from, their light falling in after you. But you would also see something new. You would be in a region of space-time where the direction out no longer exists. All paths, every single road you could possibly take, lead inward. Now, pause for a moment. Look at the room around you. Look at the sky if you can see it. We live in a universe that appears to have a beginning, the Big Bang, and creates an expanding bubble of space. We look out and we see galaxies rushing away from us. We look back in time and we see a dense, hot past. But we also have a horizon. It is called the cosmological horizon or the Hubble volume. There is a limit to how far we can see, a limit defined by the speed of light and the age of the universe. Things beyond that horizon are disconnected from us. We cannot send them a signal that will reach them today. They are effectively separated from our causality. This is where the first ghost of the theory appears. In the 1970s, physicists began to play with the numbers. They looked at the Schwarzschild radius, that is the mathematical formula that tells you how big a black hole would be for a given amount of mass. If you take the mass of the Earth and crush it into a black hole, it would be the size of a peanut. If you take the Sun, it would be a few kilometers across. But the equation has a strange property. As the mass grows, the density required to make a black hole decreases. A small black hole must be incredibly dense, but a giant one, a black hole the size of a galaxy, it would be as thin as air. And if you keep going, if you take all the mass we estimate exists in our observable universe, every star, every galaxy, every cloud of gas, every photon of light, and you plug that number into the Schwarzschild equation, do you know what radius you get? You get the radius of our universe. This is not a metaphor. The math suggests that the observable universe is exactly the size it would be if it were a black hole containing all its mass. We are living at the critical density. To a physicist, this is a coincidence that keeps them awake at night. Why would the universe, which we think of as a creation event, perfectly mimic the geometry of a collapse event? It suggests that perhaps the event horizon isn't just something out there in the dark, surrounding distant dead stars. It suggests the event horizon is here, that it is the container of our reality, that we are already inside. This idea, known as black hole cosmology, flips our perspective upside down. It implies that the Big Bang wasn't a unique explosion that happened in the middle of nothingness. Instead, it implies that our beginning was actually an event that happened in a parent universe. In that larger, older place, a massive star collapsed. It fell in on itself, tearing a hole in the fabric of its own space-time. To the observers in that parent universe, it looked like a black hole forming, a dark sphere of silence. But on the inside, that collapse created a region of intense heat and density that suddenly expanded outward, creating a new bubble of space-time. That bubble is us. We are the aftermath of a collapse in a higher dimension. It changes how we feel about the dark. We often fear the cold, empty spaces between the stars. But if this theory is true, that darkness is not a void. It is the walls of a womb. We are nesting inside a protective shell that separates us from a larger, perhaps far stranger, cosmos. The event horizon is not a prison. It is a cradle. As we drift deeper into this series, we are going to explore the mechanics of how this could work. We need to talk about what happens at the center of a black hole, at the so-called singularity, and why modern physics is desperate to get rid of it. We need to talk about time and why it only moves forward for us, just as it only moves inward for a black hole. But for now, just hold this image. The universe is not an infinite sheet of paper. It is a bubble, a sphere of existence floating in a much larger sea. And we, with all our history, our wars, our loves, and our science, are the internal dreams of a sleeping giant. The horizon is the limit of our dream. And tonight, we are going to try to see past it. When we try to tell the story of the universe, we usually start with the phrase, "in the beginning." It is a comfortable way to start a story. It implies a clean slate, a moment when the clock started ticking, when space unfurled like a fresh tablecloth. We call this moment the Big Bang. And for the last 100 years, the Big Bang Theory has been the champion of cosmology. It explains the expansion of the galaxies. It explains the heat left over in the background radiation. It explains the ratio of hydrogen to helium in the stars. It is a masterpiece of scientific deduction. But there is a flaw, a crack in the lens. And that flaw is hidden in the very first fraction of a second. If you run the movie of the universe backward, everything gets closer together. Galaxies merge. Stars dissolve into gas. The gas gets hotter and denser. Eventually, all the matter and energy in the cosmos is squeezed into a space smaller than an atom, smaller than a proton, until finally, it reaches a point of zero volume and infinite density. This point is called a singularity. And while it sounds impressive, in physics, a singularity is not a triumph. It is a failure. When an equation gives you an answer of infinity, it is the universe's way of saying, you don't understand what is happening here. Infinite density is impossible. Infinite heat is impossible. The laws of physics, as we know them, general relativity, which governs gravity, and quantum mechanics, which governs particles, break down completely at a singularity. They scream at each other. They stop making sense. So the standard Big Bang Theory leaves us with a mystery. Meaningful physics essentially starts a tiny moment after the beginning. The actual moment of $t equals $0 is a blank page. We don't know what triggered it. We don't know why it exploded. We just know that it did. Now, let's shift our gaze from the beginning of time to the end of a star's life. When a massive star runs out of fuel, it can no longer support its own weight. The gravity of its own mass crushes it inward. The core collapses. The outer layers are blown away, but the center falls in on itself. And according to Einstein's general relativity, if that mass is heavy enough, nothing can stop it. The star shrinks past the size of a planet, past the size of a city, past the size of a pinhead. And where does it stop? Einstein's math says it doesn't. It collapses down to a point of zero volume and infinite density. Does that sound familiar? It is the exact same problem. The singularity at the beginning of the universe and the singularity at the center of a black hole are mathematical mirrors of each other. One is a singularity in the past, from which everything emerged. The other is a singularity in the future, into which everything falls. This similarity is too striking to be an accident. It suggests that the Big Bang and black holes are not two different phenomena, but the same process viewed from two different perspectives. But this brings us back to the failure of the singularity. Nature rarely deals in infinities. Usually, when our math says infinite, it means we are missing a piece of the puzzle, some force or mechanism that kicks in at the last moment to prevent the impossible from happening. This is where the idea of a black hole universe begins to solve the problems that the standard Big Bang cannot. Imagine the star collapsing in that parent universe we spoke of. It is falling inward, crushing down. But instead of shrinking to a magical point of nothingness, what if it hits a limit? What if space-time itself has a texture, a graininess, or a resistance that we don't see on large scales? There are theories like loop quantum gravity or the Einstein-Cartan theory, which we will explore deeply later, that suggest space-time is not perfectly smooth. When you squeeze it too hard, it pushes back. Twists. So the star collapses. It gets smaller and smaller, billions of tons crushing down. But just before it reaches that impossible singularity, the fabric of space-time snaps. It resists. The collapse halts abruptly and then rebounds. Think of a ball dropped from a great height. It hits the pavement and compresses. For a split second, it is squashed. And then, the elastic energy releases, and it flies upward in the darkness of the black hole. The collapsing matter bounces. But it can't bounce back out into the parent universe. The gravity is too strong. The door is closed behind it. The event horizon has already formed. So where does the energy go? It has nowhere to go but in. Carves out a new region of space-time. It expands violently, not into the space it came from, but into a new dimension of growth. To the outside observer in the parent universe, the star has simply gone silent. It has become a black hole, a heavy, dark object. They see only the gravity. They don't see the bounce. But inside the bounce is the Big Bang. The explosion that created our universe was not a creation from nothing. It was the recoil of a massive collapse. The infinite heat and density we see in our past was the moment of the bounce, the moment the falling matter from the parent universe hit the bottom of the fabric of reality and sprang back. This solves the problem of the singularity. There was no infinite point. There was a moment of maximum density, yes, but it was finite. It was understandable. It was simply a transfer of energy from one place to another. This perspective creates a profound connection. It means that our Big Bang is not a unique, one-off miracle. It is a mechanism. It is happening right now in our own universe millions of times. Every time we see a massive star die and collapse into a black hole, we might be witnessing the birth of a new universe. Hidden away behind a veil of gravity, we are looking at the backs of new worlds. But if this is true, it raises a question that makes the brain ache with vertigo. If we are inside a black hole, and that black hole was made by a collapsing star in a parent universe, then is that parent universe also inside a black hole? Is it turtles all the way down? An infinite nesting doll of universes, born from the deaths of stars, stretching back forever. And what does that make us? Are we just a byproduct of stellar evolution? Or are we part of a reproductive system of the cosmos? The singularity was the flaw that cracked the door open. It showed us that our physics was incomplete. But by stepping through that door, by accepting that the singularity is actually a bridge, we find ourselves in a much larger, much stranger room. A room where universes are not islands, but children. As we move to the next part of our journey, we need to ask, how does this bounce actually happen? What is the force strong enough to stop the collapse of a star? To understand that, we have to talk about something Einstein ignored, but which might be the secret ingredient of reality, the spin of space-time itself. In the silence of deep space, everything spins. Planets rotate on their axes as they drift through the void. Stars spin as they burn, some leisurely, others with the frantic speed of a pulsar. Galaxies, those island universes containing billions of suns, rotate with a majestic slowness that takes hundreds of millions of years to complete a single turn. Even the tiniest particles, the electrons and quarks that make up the atoms in your body, possess a quality physicists call spin. It seems to be the fundamental dance of reality. Angular momentum is the engine of the cosmos. And yet, when Albert Einstein first wrote down the equations for general relativity in 1915, the equations that gave us our modern understanding of gravity, he left something out. He described gravity as the curvature of space-time, like a heavy ball sitting on a trampoline, bending the fabric so that other objects fall toward it. It was and remains a beautiful theory. It explains the orbit of Mercury, the bending of light by stars, and the expansion of the universe. But in its original form, it assumed that space-time was smooth and simple. It ignored the spin. For decades, this omission didn't seem to matter much. On the scale of planets and solar systems, the curvature of space is the dominant force. The spin of the matter inside it is negligible. But when you look at the center of a black hole, at that terrifying point where a star is crushed down to nothing, the omission becomes a catastrophe. This is where the singularity appears, the mathematical error of infinite density we spoke of earlier. It appears because the theory is missing a piece of the puzzle. It is missing the resistance. Enter the Einstein-Cartan theory. Later in the 20th century, physicists realized that to describe the universe truly, you cannot just look at mass. You must look at spin. They extended Einstein's relativity to include a property called torsion. If gravity is the curving of the space-time fabric, torsion is the twisting of it. Imagine wringing out a wet towel. You are not just bending the cloth. You are twisting its fibers. This seemingly small addition changes everything. In the vacuum of space, torsion does nothing. It is a ghost force, invisible and weak. But inside a black hole, inside matter that is being crushed to densities trillions of times greater than atomic nuclei, torsion wakes up. And when it wakes up, it is powerful. According to theoretical physicist Nikodem Poplawski, who has championed this idea, torsion acts as a repulsive force. It is the anti-gravity of the quantum world. When matter is squeezed too tightly, its intrinsic spin pushes back against the crushing weight of gravity. It says, no, let us go back to that collapsing star in the parent universe. The gravity is overwhelming. The core is shrinking. The event horizon has formed, sealing the star off from the outside world. To the parent universe, the star has died. But inside, the drama is just beginning. The matter falls inward, faster and faster, crushing down toward the center. In standard physics, it hits the singularity and vanishes. But in a universe with torsion, something else happens. As the density creates a pressure cooker of unimaginable proportions, the space-time fabric begins to twist violently. The torsion builds up, pushes back against the gravity. It is a cosmic arm-wrestling match between the weight of a star and the geometry of space itself. And eventually, torsion wins. The collapse stops. It does not hit zero size. It reaches a minimum radius, extremely small, incredibly dense, but finite. The kinetic energy of the falling star, having nowhere else to go, is converted into a massive repulsive push. The collapse reverses. The star bounces. This is the big bounce. But remember, this bounce is trapped. The gravity of the black hole is still pulling everything in from the perspective of the outside. The bouncing matter cannot go back out through the event horizon, cannot return to the parent universe. So it does the only thing it can: it creates new space. It expands inward, creating a new volume of space-time that grows larger and larger, fueled by the immense energy of the bounce. A consciousness riding on that wave of expansion, the universe would appear to be cooling and growing. The density would drop. The twist of torsion would fade away as the matter spread out, leaving behind only the smooth curvature of gravity we see today. The chaotic, hot, dense soup of the bounce would settle into hydrogen, helium, stars, and galaxies. Does this sound familiar? This is our history. This is the Big Bang. What we call the beginning of time, was actually the moment the torsion force overcame gravity in the heart of a parent black hole. We are the expanding breath of a dying star. This hypothesis, often called cosmology with torsion, is elegant because it removes the impossible. There is no singularity. There is no point where physics breaks down. There is only a transfer. And it implies that our universe has an inheritance. The rotation of that parent star, the spin that generated the torsion, might still be imprinted on our cosmos today. It suggests that our universe might have a preferred direction, a subtle rotation left over from its birth. When we look at the distribution of galaxies, at the faint glow of the radiation left over from the bounce, we might be searching for the fingerprints of our mother star. This view changes the nature of black holes from destroyers to creators. In this model, every black hole in our own universe, every single one formed by the death of a massive star, is doing the exact same thing. It is not crushing matter into nothingness. It is squeezing it until it bounces, birthing a new, baby universe on the other side of its horizon. We are living in a family tree of universes. We are likely the child of a black hole and the parent to trillions more. The geometry of the cosmos is not a flat, dead stage. It is a breathing, reproducing system, and the mechanism of that breath is the simple, elegant twist of space-time itself. But if we are the interior of a black hole, what does that make the Big Bang from the perspective of time? If a black hole is a place where things only fall in, why do we see a universe where everything is rushing out? To understand that, we have to look in the mirror. We have to talk about the white hole. In the strange logic of general relativity, equations often work in two directions. If you have a mathematical description of a process, you can usually reverse the variable for time, swapping future for past. And the equation still holds true. It describes a physical possibility, even if we haven't seen it with our own eyes. When physicists first looked at the math of a black hole, they saw a region of space where gravity is so strong that nothing, not even light, can escape. The event horizon is a one-way membrane. You can go in, but you can never come out. Matter falls toward the center, toward the future. But if you take that video and play it backward, if you reverse the flow of time in the equations, you get an object that is mathematically perfectly valid, but physically opposite. You get a region of space that nothing can enter. A region where light and matter can only move outward. A place that spews energy and light into the universe but refuses to let anything in. This object is called a white hole. For a long time, white holes were considered mathematical curiosities, ghosts in the machine of Einstein's theory. We have never seen one in our telescopes. We don't see massive bright objects spontaneously erupting in the sky, repelling everything that tries to touch them. Because of this absence, many scientists dismiss them as fiction. But if the hypothesis we are exploring is correct, that our universe is the interior of a black hole, then we might have been looking at a white hole all along. We just didn't recognize it because we are living inside it. Think about the Big Bang again. What was it? It was a moment in time, roughly 13.8 billion years ago, when all matter and energy suddenly rushed outward from a single dense point. It was an event that only allowed motion in one direction: expansion. You cannot travel back to the Big Bang. You cannot throw a rock at the Big Bang. It is a point in the past that repels us simply by the flow of time and space. This matches the definition of a white hole perfectly. The connection between the two concepts is the bounce we discussed. The theory suggests that a black hole and a white hole are actually the same object, seen from different sides of the event horizon. Imagine the star in the parent universe collapsing. It falls into the black hole. It crosses the horizon. To the parent universe, it is gone. But as we learned, the torsion of space-time stops the collapse and causes a rebound. That rebound, that explosion of matter creating a new space-time, is the white hole. So the black hole is the entry wound in the fabric of the multiverse, and the white hole is the exit wound. But the exit doesn't lead back to the parent universe. It leads here. It leads to the creation of our reality. This resolves the paradox of why we don't see white holes floating around in space. A white hole isn't an object that sits in a galaxy like a star. A white hole is a moment. It is the birth cry of a universe. It is the transient, explosive event that sets the arrow of time in motion. This concept creates a beautiful symmetry in time. In a black hole, all paths lead to the future singularity or the bounce. In a white hole, all paths lead away from the past singularity. We are caught in the current between these two poles. We are flowing away from the white hole of our birth, carried by the expansion of space. But this mirror image brings up a troubling thought about thermodynamics. In our universe, we have a law that feels absolute. The second law of thermodynamics. It states that entropy, a measure of disorder, always increases. Things break, eggs shatter, stars burn out, coffee cools down. Time has an arrow, and it points toward disorder. A black hole is the ultimate entropy machine. Physicists Stephen Hawking and Jacob Bekenstein showed that black holes contain massive amounts of entropy. They are arguably the most disordered objects in the universe. But a white hole by definition, spits out highly organized matter. It is a point of low entropy, and this matches our universe too. The Big Bang was incredibly smooth, uniform, and organized. It was a state of incredibly low entropy. If it hadn't been, stars and galaxies and life could never have formed. We are living off the savings account of orderliness that the Big Bang provided. So, the mechanism of the black hole universe offers a solution to one of the biggest questions in science. Why did the universe start with such low entropy? Perhaps the filtering process of the event horizon is responsible. When matter falls into a black hole in the parent universe, the information it carries is scrambled, yes. But the energy that bounces, the raw stuff that makes our universe, comes through in a state that allows for a fresh start. The event horizon acts as a scrubber, a reset button for the arrow of time. This implies that while the parent universe might be old, filled with dead stars and high entropy, the child universe gets to be young. It gets a blank slate. The white hole is the injection of fresh possibility into reality. We are the other side of the mirror. When we look at a black hole in our own galaxy at Cygnus X1 or Sagittarius A*, we are looking at the intake valve of a new reality. And somewhere on the other side of that darkness, in a space we can never reach, a Big Bang is happening. A new white hole is flaring into existence, perhaps seeding a universe with its own laws, its own stars, and its own observers wondering where they came from. But if we are inside a projection of a higher dimensional collapse, is our reality real? Or is it a hologram? The math of black hole surfaces suggests something even stranger than a bounce. It suggests that everything we know, the 3D world, your body, this planet, might be a projection of information stored on the distant 2D surface of the horizon itself. To understand this, we must turn to the holographic principle. Imagine for a moment that you are standing in a vast ancient library. The shelves stretch up into the darkness, disappearing into the shadows above. Millions of books are lined up, each one containing a unique story, a unique set of instructions, a unique universe of information. Now, imagine you want to know how much information this library can hold. Your instinct would be to measure the volume of the room. You would calculate the height, the width, and the depth. You would figure out how many cubic meters of air exist inside, and then calculate how many books can fit into that three-dimensional space. It makes sense. In our daily lives, capacity is about volume. A bucket holds water because it has depth. A box holds toys because it has space inside. But when physicists began to study black holes in the 1970s, they stumbled upon a realization that shattered this intuitive understanding of space. They discovered that the universe does not store its deepest secrets in the volume of a room. It stores them on the walls. This realization began with a simple question about entropy. As we discussed, entropy is a measure of disorder or hidden information. If you throw a book into a black hole, the information in that book, the words, the structure of the paper, the ink, seems to vanish from the observable universe. But quantum mechanics says information cannot be destroyed. So where does it go? Jacob Bekenstein and Stephen Hawking found the answer. The information isn't lost. It is encoded onto the surface of the black hole, onto the event horizon itself. Here is the shock. The amount of information a black hole can hold, its entropy, does not grow as its volume gets bigger. It grows as its surface area gets bigger. If you double the size of the event horizon sphere, you don't quadruple the information capacity. You increase it by the square. The math says clearly that the interior volume doesn't matter. The only thing that counts is the skin. This led to the holographic principle. A hologram, as you might know from credit cards or science fiction movies, is a two-dimensional sheet of plastic. It is flat, but when light shines through it, it produces a three-dimensional image. The image looks real. It has depth. You can walk around it and see different angles. But if you try to touch the image, your hand goes through it. The reality of the object is entirely stored on the flat 2D surface. The 3D appearance is a projection. Now, apply this to the black hole universe hypothesis. If we are living inside a black hole, our entire universe, the galaxies, the stars, the empty space, and even you sitting there right now, might be a holographic projection. The real data, the fundamental bits of information that describe our reality, may be plastered on the inside surface of the event horizon, billions of light years away at the edge of the cosmos. This implies that space itself, the depth we feel when we look at the stars, might be a sophisticated illusion. We perceive three dimensions, up and down, left and right, forward and backward. But these might be emergent properties, generated by the interactions of information on a two-dimensional shell. We are the ghosts in the machine. We are the songs being played from a vinyl record, thinking the music is floating in the air, when in reality, it is etched into the grooves of the disc. This thought can be dizzying. It suggests that every point in our universe is connected to a specific point on the distant horizon. It suggests that the pixel size of reality is incredibly small, something called the Planck length. If you zoom in far enough on space, you won't find smooth emptiness. You will find grains. You will find bits of information, like the zeros and ones of a computer code, shimmering on the boundary of existence. Why does this matter for the theory that we are in a black hole? Because it solves the problem of room. A black hole interior is mathematically finite, yet our universe appears effectively infinite or at least remarkably vast. The holographic principle allows a bounded surface to contain a world that feels boundless to the inhabitants inside. We might be walking on a treadmill of space, moving through a projection that updates constantly, giving us the experience of a vast cosmos while we are actually mathematically pinned to the walls of a black star. There is a haunting beauty in this. It means that the event horizon, that line we usually fear as the point of death, is actually the hard drive of our reality. It is the memory of the universe. Everything that falls into the parent black hole adds to the surface area of the horizon. As the parent black hole grows, feeding on the matter of the higher universe, our horizon expands. Our hard drive gets bigger. The universe cools. The pixels get stretched. Perhaps the expansion of the universe, which we measure with our telescopes, is simply the growth of the event horizon in the parent universe. As it eats, we grow. As it consumes stars and gas, our capacity for complexity increases. We are directly tied to the feeding habits of the monster that contains us. And if this is true, it changes the definition of us. We are not solid lumps of matter floating in a void. We are the interplay of information. We are stories written on the sky, projected inward to create the sensation of a life. The horizon is not a wall that keeps us in. It is the canvas upon which we are painted. This perspective aligns with some of the deepest mysteries of quantum physics, specifically the way particles can be entangled over vast distances. If two particles on opposite sides of the universe are instantaneously connected, it breaks the rules of 3D space. But if they are just 2 points on a 2D sheet that are actually right next to each other in the source code, the mystery vanishes. The distance is the illusion. The connection is the reality.so. As you look at the dark spaces in your room tonight, remember that space might not be empty. It might be full of code. And the edge of the universe, that silent, unreachable horizon, is busy writing the script of this very moment. We are the reading of that script. We are the light shining through the film. And as long as the horizon holds, the movie continues. But if our universe is a projection or a bubble inside a black hole, we still have to answer the question of why. Why is the movie so perfect? Why are the laws of physics tuned exactly right to allow stars, carbon, and life to exist? Is it luck? Is it design? Or is it something much more organic? To answer that, we have to stop thinking of universes as rocks and start thinking of them as living things that evolve. One of the most stubborn questions in science is the Goldilocks enigma. When we measure the fundamental constants of nature, the strength of gravity, the mass of the electron, the strength of the atomic forces, we find something suspicious. They are perfect. They are balanced on a knife edge. If gravity were slightly stronger, stars would burn out in millions of years instead of billions, leaving no time for life to evolve. If it were slightly weaker, stars would never ignite at all, and the universe would remain a cold, dark fog of hydrogen. If the strong nuclear force were a tiny bit different, carbon, the backbone of all life we know, could not form in the hearts of stars. It feels like the universe was built for us. For centuries, this fine-tuning was used as an argument for a designer. It seemed too precise to be an accident. In modern times, many scientists invoke the multiverse or the anthropic principle, saying, well, there are infinite universes with random laws, and we just happen to be in the one where we can survive to ask the question. It's a logical answer, but it feels unsatisfying. It feels like shrugging our shoulders and saying, it's just luck. But what if it isn't luck? What if it isn't design? What if it is evolution? In the 1990s, the theoretical physicist Lee Smolin proposed a daring hypothesis called cosmological natural selection. He looked at the black hole theory we have been discussing and realized it offered a mechanism for evolution on a cosmic scale. Think about how natural selection works in biology. You need three things: reproduction, mutation, and selection. An organism makes a copy of itself, reproduction. Sometimes the copy has a slight random change, mutation. If that change helps the offspring survive and reproduce more, the trait spreads, selection. Over billions of years, this simple process turns single-celled slime into eagles, whales, and humans. Smolin argued that universes do the same thing. If our universe is inside a black hole, and if every black hole we create gives birth to a new universe, then universes reproduce. The offspring universe is born from the singularity or the bounce of the parent. Here is the key. Smolin suggested that when this bounce happens, the fundamental laws of physics don't stay exactly the same. They mutate. The extreme pressures and temperatures of the bounce cause the constants to shift by a tiny, random amount. Maybe gravity gets a fraction of a percent stronger. Maybe the electron gets a little lighter. This creates a cosmic family tree. Some universes will be born with bad genes. Maybe their gravity is too weak to form stars. In those universes, matter just floats apart. No stars means no collapse. No collapse means no black holes. No black holes means no offspring. That universe is a dead end. It is sterile. But other universes will be born with good genes. They have laws that encourage clouds of gas to collapse into stars. They produce billions of massive suns. Those suns die and form billions of black holes. Each of those black holes births a new universe, passing on those same star-friendly laws. Over distinct eons of time, the multiverse would fill up with universes that are optimized for one specific purpose: the production of black holes. The sterile universes would die out, and the fecund universes would dominate the population. It is exactly like bacteria filling a petri dish. Now, look at our universe. What is it good at? It is incredibly good at making stars, produces them by the trillions, and it is incredibly good at letting those stars die and collapse. We have observed stellar mass black holes everywhere. We have supermassive black holes in the center of nearly every galaxy. Our universe is a black hole factory. It is a reproductive champion. This is where the twist comes for us, for life. It turns out that the conditions required to make a lot of black holes are almost exactly the conditions required to make life. To make a black hole, you need massive stars. To make massive stars stable enough to burn and then collapse, you need a balance of gravity and nuclear forces. You need carbon and oxygen to help cool the gas clouds so they can condense. You need a universe that lasts a long time, billions of years, so the galaxies can evolve. Guess what life needs? We need massive stars to forge the elements in our bodies. We need carbon and oxygen to build our cells. We need stable planets. We need billions of years for evolution to work. I end this theory. We are not the purpose of the universe. We are not the specially chosen residents of a house built for us. We are essentially a side effect. We are cosmic mold growing on the machinery of a black hole factory. The universe is tuned for carbon and stars because that is how it reproduces. The fact that carbon and stars also happen to make humans, giraffes, and trees is just a happy accident of chemistry. We are like parasites living in the womb of a creature that is trying to have babies. This might sound humbling, even diminishing, It removes us from the center of the stage. But there is a grandeur in it, too. Connects us to the deep, deep history of reality. It means that the laws of physics we study are not cold, arbitrary numbers written in stone. They are the result of an ancestry. They are the survivors of a cosmic struggle for existence that has been going on for timelines we cannot comprehend. Gravity is the way it is because it worked. The speed of light is the speed it is because it allowed our ancestors to survive. We are living in a universe that is a winner, and it implies something about the future. If we are efficient at making black holes, are we contributing to this cycle? Every time a star collapses in the Milky Way, are we unwittingly helping to launch a new experiment in reality? Are we the midwives of the multiverse? But there is a darker implication, too. If this theory holds, then the universe is not just expanding. It is competing. And there are forces at work, like the mysterious dark energy pushing the galaxies apart, that might be part of this evolutionary pressure. Is dark energy a mechanism to stop the universe from collapsing too soon? Or is it a sign that our parent universe is growing, pulling us apart as it expands? To understand the acceleration of the cosmos, we have to look at the illusion of expansion and ask, are we really moving apart, or are we just falling deeper into the hole? When we look out into the deep ocean of the night sky, we are met with a paradox that has troubled astronomers for nearly a century. The universe is not sitting still. It is moving, and it is not just moving. It is running away from itself. In the late 1920s, Edwin Hubble discovered that the galaxies are receding from us. The farther away they are, the faster they go. This was the first great shock. The universe is expanding. For decades, we assumed that this expansion was a leftover push from the Big Bang, like a car coasting on a highway after the engine has been turned off. We assumed that gravity, the great pull of all matter, would eventually slow this expansion down. We thought the universe would gradually hit the brakes. The only question was whether it would stop completely and fall back in on itself, or if it would just drift apart slowly forever. But in 1998, two teams of astronomers looked at distant exploding stars, type Ia supernovae, to measure this deceleration. They expected to see the universe slowing down. Instead, they found something that made no sense. The universe wasn't slowing down. It was speeding up. The galaxies were rushing away faster today than they were yesterday. It was as if someone had pressed the accelerator pedal to the floor billions of years after the car had started moving. To explain this, scientists invented a placeholder name for the unknown energy driving this acceleration. They called it dark energy. It is calculated to make up roughly 68% of the total energy in the cosmos. It is everywhere, pushing space apart, overcoming gravity. But what is it? We don't know. In the standard model, it is just a number, a cosmological constant that we have to plug into the equations to make them work. It feels arbitrary. It feels like a patch. However, if we shift our perspective and accept the possibility that we are living inside a black hole, dark energy stops being a mystery force and starts being a geometrical consequence. It stops being a thing and becomes an illusion of perspective. Let's go back to our parent black hole. Remember, we are theoretically living inside the event horizon of a massive object in a larger universe. Black holes in that parent universe are not static statues. They are active eaters. They grow. Imagine the parent star that formed our black hole universe. It sits in a galaxy in that higher dimension. It is surrounded by gas, dust, and light. Over time, matter falls into it. Maybe it swallows a neighboring star. Maybe it drifts through a cloud of hydrogen. As it eats, its mass increases. Now, look at the Schwarzschild equation again. The radius of a black hole is directly proportional to its mass. If you add mass to a black hole, the event horizon gets bigger. The sphere expands. What happens to the interior volume when the surface grows? It expands. If our universe is the interior of that black hole, and the parent black hole is feeding, then our universe must expand. We would perceive this growth not as walls moving outward, but as space itself stretching, carrying the galaxies with it. And here is the crucial connection. If the parent black hole eats something massive, say it merges with another black hole, its growth would not be steady. It would be rapid. It would accelerate. So when we look at dark energy and see the galaxies rushing apart, we might not be seeing a mysterious anti-gravity force generated by nothingness. We might be witnessing the dining habits of our parent. The acceleration of our universe could correspond to a period in the parent universe where our black hole is falling into a dense region of space, gobbling up matter at an increasing rate. We are feeling the growth of our container. There is another, perhaps even more vertigo-inducing interpretation of dark energy within this theory. It has to do with falling. Einstein's equivalence principle tells us that acceleration and gravity are indistinguishable. If you are in a windowless elevator in deep space and a rocket pushes it, you feel pressed to the floor. It feels exactly like gravity. Conversely, if you are falling freely toward a planet, you feel weightless. If we are inside a black hole, we are all, in a sense, falling toward the boundary. But because space is curved so severely, falling doesn't look like moving down. It looks like the space around you is stretching. Some physicists have proposed that what we call the expansion of the universe is actually a mirage caused by the fact that we are looking at the universe from the inside of a gravity well. When we look at distant galaxies, we are looking at objects that are at different depths of this well. The light coming from them is being distorted by the extreme geometry of the black hole interior. This distortion creates an optical illusion. It makes objects look dimmer and farther away than they would be in flat space. When astronomers in 1998 measured those supernovae, they found they were dimmer than expected. They interpreted this as the stars being farther away, pushed by dark energy. But in a black hole universe, they would be dimmer simply because the light is struggling against the geometry of the interior. We might be mistaking the shape of the room for the movement of the walls. This reinterpretation is comforting in a strange way. Dark energy is terrifying because it implies a lonely future. If it keeps pushing, eventually the galaxies will be so far apart that the sky will go dark. Stars will die and they will never be replaced. The universe will end in a big freeze, a cold, empty void where nothing ever happens again. But if dark energy is just the growth of the parent black hole, the story changes. The growth isn't infinite emptiness. It is the accumulation of more material. We are not dissolving into nothing. We are receiving new potential. And there is a third possibility, one that links back to the white hole idea. If we are expanding because we were bounced out of a collapse, the acceleration could be the final release of that torsion spring we talked about. We are like a diver who has just pushed off the board. The acceleration is the release of stored energy. In all these scenarios, the mystery of dark energy stops being a magical number we can't explain. It becomes a physical part of the machine. It tells us that our universe is connected to something outside itself. We are not a closed box. We are a dynamic system, reacting to the conditions of a place we can never see. But while dark energy is a clue hidden in the movement of galaxies, there is another clue hidden in the light itself. A clue that suggests the universe has a top and a bottom, a direction in space that shouldn't exist. It is a pattern so strange that when scientists first found it, they thought their equipment was broken. They called it the axis of evil, and it might be the smoking gun of the black hole theory. The most ancient light in the universe is not from a star. It is a glow that comes from everywhere at once, a faint hum of microwave radiation that fills every cubic centimeter of space. It is called the cosmic microwave background, or CMB.to. Understand the CMB? You have to imagine the universe just 380,000 years after the Big Bang. Before that moment, the cosmos was a hot, dense fog of plasma. It was like the inside of the sun, opaque and glowing. Light couldn't travel more than a few inches before hitting a particle. But as the universe expanded and cooled, there came a specific moment when the temperature dropped enough for atoms to form. The fog cleared. The light was suddenly free to travel. That light has been traveling for 13.8 billion years. It has stretched as the universe expanded, shifting from visible light down to microwaves. Today, we can detect it with radio telescopes and satellites. It is the baby picture of our universe. When scientists first mapped this light in the 1990s with the COBE satellite, and later with WMAP and Planck, they expected to see a random pattern. The Big Bang theory says the universe should be isotropic, which means it should look roughly the same in every direction. There should be no north or south in space. The splotches of slightly hotter and slightly colder spots in the CMB should be scattered randomly, like static on an old television screen. But when the data came back, the scientists stopped breathing. The spots weren't random. They found that the hot and cold patches in the cosmic microwave background seemed to line up. There was a weird alignment, a preferred direction that stretched across the entire sky. It looked as though the universe had an axis, a giant, invisible rod running through the cosmos, around which the temperature fluctuations were organized. This shouldn't happen. In a standard Big Bang explosion, everything pushes out equally. There is no reason for the left side of the universe to coordinate with the right side. The odds of this alignment happening by pure chance were calculated to be less than 1 in 1,000. The scientists were so disturbed by this anomaly that they gave it a dramatic name: the axis of evil. Evil, not because it is malevolent, but because it threatens to destroy the standard model of cosmology. It breaks the Copernican principle, the idea that we are not in a special place or orientation. For years, skeptics argued that the axis was a mistake. Maybe it was dust in our own solar system. Maybe it was a glitch in the satellite. Maybe it was just how the math was processed. But mission after mission confirmed it. The Planck satellite, launched by the European Space Agency, mapped the sky with incredible precision in 2013. The axis was still there. The universe has a structure. It has a direction. Now, bring in the black hole universe hypothesis. Does it explain the axis of evil? Yes, and it does so effortlessly. Remember the parent star, the star that collapsed to form the black hole we live in. Stars in the universe spin. They rotate. When a star collapses, that rotation doesn't disappear. Conservation of angular momentum dictates that as the star gets smaller, it spins faster. Inside the black hole, the space-time fabric is dragged around by this spin. This is a known phenomenon in general relativity called frame dragging or the lens stirring effect. If you are inside a rotating black hole, a Kerr black hole, space itself is twisting like a vortex. If our universe was born inside a spinning black hole, it would inherit that spin. The Big Bounce wouldn't just be an outward explosion. It would be a spiraling explosion. The entire cosmos would have a slight, imperceptible rotation inherited from its mother. The axis of evil, then, is simply the axis of rotation of the parent black hole. When we look at the cosmic microwave background, we are seeing the imprint of that primordial twist. The hot and cold spots align because the space-time they are traveling through has a grain, a directionality caused by the spin. We are not living in a random ball of fire. We are living in a gyroscope. This alignment also explains another mystery in the CMB called the cold spot. There is a massive region in the southern hemisphere of the sky that is significantly colder than it should be. It is a giant void. In the standard model, it is a statistical fluke. But in a rotating black hole universe, such spots are expected. They are the poles of the torsion field, regions where the expansion dynamics are slightly different due to the geometry of the spin. This implies that when we look up, we can actually point to the North Pole of the universe. We can orient ourselves relative to the greater cosmos outside our horizon. It creates a terrifyingly physical picture of our reality. We are not floating in an abstract void. We are inside a physical object with a shape, a spin, and an orientation. We are spinning inside a shell that is spinning inside a galaxy in a universe we will never see. This rotation might even be responsible for the fact that galaxies themselves spin. In the standard model, it is hard to explain where galaxies got the energy to start rotating so fast. But if the whole universe was born spinning, then galaxies are just small eddies in a massive universal whirlpool. They are spinning because the whole ocean is turning. The axis of evil is a ghost. It is a fossil of the motion that created us. It is the universe whispering to us that it is not a random accident, but a structured object. And if it has a structure, it likely has a boundary. But if the universe has a beginning, the bounce, and a structure, the spin, does it have an end? Or does it just wind down? This brings us to the problem of time itself. Why does time only move forward? In the equations of physics, you can play the movie backward and it makes sense. But in real life, you can never unbreak an egg. You can never unsay a word. To understand the fate of our black hole universe, we have to understand the engine that drives time. We have to talk about entropy and why the arrow of time might be pointing us toward a specific destination on the horizon. Time is the invisible river that carries us all. We feel it in the beating of our hearts, in the graying of hair, in the crumbling of stone. We understand intuitively that time has a direction. It moves from the past, which is fixed and remembered, toward the future, which is open and unknown. You can scramble an egg, but you can never unscramble it. You can burn a log into ash, but you can never turn the ash back into a log. This directionality is strange because, as we touched on earlier, the fundamental laws of physics, Newton's laws, Einstein's relativity, Schrödinger's equation, are time-symmetric. They work equally well forward or backward. If you zoom in to a single collision between two atoms, you cannot tell if the movie is playing forward or in reverse. The physics is identical. So where does the arrow come from? If the atoms don't care about time, why do we? The answer lies in the second law of thermodynamics, the law of entropy. Entropy is often described as disorder, but a better way to think of it is probability. There are millions of ways for a deck of cards to be shuffled and messy. There is only one way for it to be perfectly ordered by suit and number. Because the messy states vastly outnumber the ordered state, if you shuffle the deck, you will naturally move from order to disorder. You move toward the state of highest probability. The universe started in a state of incredibly low entropy, the Big Bang. Since then, it has been sliding down the slope toward high entropy. That slide is what we experience as the flow of time. Now, let's place this arrow inside our black hole universe. If we are living inside a black hole, the behavior of entropy takes on a sinister geometric meaning. In the 1970s, Stephen Hawking and Jacob Bekenstein proved that a black hole has entropy. In fact, it has the highest possible entropy for an object of its size. And crucially, they proved that the entropy of a black hole is proportional to the surface area of its event horizon. The second law of thermodynamics states that the total entropy of a closed system can never decrease. It must always go up. If our universe is the interior of a black hole, this law tells us something about our container. It tells us that the event horizon, the surface area of our bubble, must effectively always be growing. This aligns perfectly with the expansion we observe. As the parent black hole in the higher universe consumes matter, its horizon grows, its entropy increases, and our universe expands. The arrow of time we feel is the growth of the event horizon. But what is the destination? Where does the river end? In a standard universe, we talk about the heat death. This is a future where entropy reaches its maximum. All the stars burn out. Black holes evaporate. Atoms decay. The universe becomes a uniform bath of cold radiation where nothing ever happens again because there is no energy difference to drive change. It is a state of perfect, frozen equilibrium. In a black hole universe, the heat death is actually thermal equilibrium with the event horizon. Imagine the parent black hole stops eating. It sits in a quiet corner of the parent universe. It eventually reaches a stable temperature. Inside, our universe would slowly settle into a state where everything matches the temperature of the horizon. We would drift toward a final silent stasis. But there is a twist. Stephen Hawking also discovered that black holes are not perfectly black. They glow. Due to quantum effects near the horizon, they slowly emit radiation, now called Hawking radiation. They lose mass. They evaporate. If a black hole loses mass, it gets smaller. Its horizon shrinks. This poses a terrifying question for us inside. If our parent black hole starts to evaporate, what happens to our universe? Do we shrink? Does the expansion reverse? Some theoretical models suggest that if the parent black hole evaporates completely, our universe would simply cease to exist as a contained entity. The walls would dissolve. The information that makes up our reality would leak out into the parent universe in a garbled stream of radiation. We would be unmade. However, this evaporation process for a large black hole takes a staggeringly long time. A black hole the mass of our observable universe would take something like 10 carat $100 years to evaporate. That is a 1 followed by 100 zeros. It is a span of time so vast that eternity feels like a brief afternoon in comparison. So, while we are technically living in a dying container, the clock is running so slowly that it is effectively infinite for us. There is another possibility, though. Some theories suggest that the interior universe detaches from the parent black hole once it is formed. The bounce creates a closed space-time that buds off, like a baby bubble pinching off from a larger soap bubble. In this scenario, the fate of the parent black hole doesn't matter to us. We have become our own independent reality, with our own physics, perhaps destined to birth our own black holes and continue the chain. But the arrow of time remains the guide. It points from the white hole of our birth toward the dark, cold equilibrium of our future. We are riding the explosion. We are the debris of a creative act that happened billions of years ago. And as we flow down this river, we carry something with us: complexity. While the universe as a whole gets messier, entropy increases. Small pockets of it can get more ordered by borrowing energy. Stars form, planets cool, life arises. You are a localized reduction in entropy. You are a knot of order in a disorderly stream. Why does the universe allow this? Perhaps because complexity is the most efficient way to increase entropy in the long run. A star burns fuel faster than a cold cloud. A black hole, the ultimate product of stellar evolution, is the supreme entropy generator. By creating us, by creating stars and black holes, the universe is fulfilling its thermodynamic destiny. It is trying to reach the end of time as efficiently as possible. We are the engines of the arrow. But if this arrow points toward the creation of more black holes, and those black holes create new universes, then time doesn't just move forward. It moves downward. It dives deeper into the rabbit hole of reality. We are not just moving toward the future, we are moving toward the next level of the simulation. This leads us to the most vertiginous thought of all. If universes give birth to universes, how far down does it go? And how far up? Are we floating in an infinite tower of realities, stacked one inside the other like Russian nesting dolls? Stand between two mirrors. Look at your reflection. You see yourself, and behind you, another reflection, and another, marching off into an infinite green tunnel of glass. It is a dizzying sight. It makes you feel small and multiplied. Now, take that feeling and apply it to the entire cosmos. If the hypothesis is correct, if our universe was born from the collapse of a star in a parent universe, logic demands that we ask, where did the parent universe come from? Was it also born inside a black hole in a grandparent universe? And does our universe, with its billions of black holes, contain billions of baby universes inside it? This is the concept of the nesting doll cosmos, or fecund universes. It suggests that reality is a fractal. A fractal is a mathematical shape that looks the same no matter how much you zoom in or out. A coastline looks like a jagged line from space. Zoom in to a bay and it's a jagged line. Zoom in to a rock and the edge is a jagged line. In this view, the universe is scale invariant. What happens on the level of stars, collapse, and black holes is exactly what happens on the level of universes, big bangs, and expansion. The structure repeats forever. This solves the problem of origins. Humans always want to know what started it all. We ask, what was before the Big Bang? If the answer is a parent universe, we ask, what started that? In a fractal cosmology, there might be no first universe. It might be infinite in both directions, an eternal chain of bubbles within bubbles, stretching back forever into the past and forward forever into the future. There is no beginning and there is no end. There is only the middle. We are always in the middle. But this nesting creates a strange situation regarding time and scale. In general relativity, time is not absolute. Gravity dilates time. The stronger the gravity, the slower time moves. We know this from the movie Interstellar, where an hour on a planet near a black hole equals 7 years in space. Now, imagine the time difference between universes. Our universe is huge. It has low density. Time here flows at a certain pace. But inside one of our black holes, that region is incredibly dense. The gravity is crushing. To an observer inside that baby universe, time might run at a completely different rate compared to us. And what about the parent universe above us? Contains the black hole we live in. To the giants living in that parent universe, our entire 13.8 billion year history might be a flash. Our Big Bang, our evolution, the rise of humans, the death of our sun, all of it might happen in the split second it takes for their star to collapse. We might be living in the blink of a Titan's eye. This scale distortion means that eternity is relative. We have all the time in the world to live our lives, but above us, barely a moment has passed. And below us, in the black holes we observe in the night sky, trillions of years of civilization could be rising and falling inside the event horizon of Cygnus X1 while we simply watch it flicker for a few nights. This idea creates a profound sense of loneliness, but also of connection. We can never communicate with the levels above or below. The event horizons are perfect soundproof walls. We are isolated in our layer of the onion, but we are intimately connected to them by the process of birth. We are made of their matter. We are shaped by their laws. And if Smolin's theory of natural selection is right, the universes below us are slightly more evolved than we are. They are better at making black holes. They are more complex. The universes above us are slightly cruder, slightly less efficient. We are a transitional form. We are a link in the chain of improvement. There is also the question of size. Is the parent universe bigger than ours? Intuition says yes, the container must be larger than the contents. But in this strange physics, size is tricky. Infinite space can be compressed into a finite package if you curve the geometry enough. It's like the TARDIS from Doctor Who, bigger on the inside. Because our universe expands, it creates new volume. It is possible that our interior is actually larger than the parent universe that spawned it, at least in terms of volume. We are growing a space that exceeds our origins. This implies that the multiverse isn't a collection of bubbles floating side by side in a void. It is a structure that grows inward, creates depth. It mines the fabric of possibility by drilling down, creating more and more room at the bottom. If you are prone to existential vertigo, look at a black hole image again. That dark disk, that shadow. You are looking at a door. And if you could walk through it, you wouldn't find a crushed star. You would find a big bang. You would find a sky full of stars, and perhaps on a planet circling one of them, a creature looking up with a telescope, wondering if its universe is inside a black hole, never realizing that you are looking at the back of its sky. This infinite regression removes the need for a creator outside the system. The system creates itself. It breathes. It grows. It is a living geometry that solves its own existence by making more of itself. But this brings us to a local question. If we are creating universes right now, where are they? Can we see them? And more importantly, are we responsible for them? If we build a particle accelerator and accidentally make a microscopic black hole, do we become God to a microscopic universe? We need to look at the baby universes we might be carrying in our own cosmic womb. We need to talk about primordial black holes and the seeds of reality scattered in the dark. The universe is not just a vast, empty room. It is a crowded, messy, and energetic place. And hidden within the folds of its history are objects that act as seeds. When we talk about black holes, we usually picture the dramatic death of a star. a massive sun running out of fuel and collapsing. These are the stellar mass black holes. But there is another kind, a kind that didn't need a star to die, a kind that might have formed in the chaotic first seconds of the Big Bang itself. These are called primordial black holes. To understand them, we have to go back to the very beginning, to the first fraction of a second after our universe bounced into existence. The cosmos was expanding violently. It was a soup of ultra-high energy particles. It was not smooth. There were fluctuations, tiny ripples in the density of the energy. In some places, these ripples were small. But in others, just by chance, the density might have been high enough that gravity took hold immediately. Before a star could ever form, before an atom could ever assemble, these pockets of pure energy collapsed under their own weight. They punched holes in the fabric of the baby universe. These are primordial black holes. They could be tiny, the size of an atom but with the mass of a mountain. Or they could be massive. And if they exist, which many cosmologists believe they do, they are scattered throughout our universe like forgotten seeds in a garden. But here is where the theory of the nesting doll cosmos gets personal. If every black hole contains a universe, then these primordial black holes are not just debris. They are siblings. They are universes that were born alongside us in the same nursery but got pinched off immediately. And what about the black holes forming right now? Every time a massive star in the Milky Way collapses, we witness a violent event. We see the supernova explosion. We detect the gravitational waves rippling out. But what we don't see is the other side. If the torsion theory holds, that collapse is creating a new region of space-time that is growing inward. We are, in a very literal sense, pregnant with billions of baby universes. This changes our relationship with the cosmos. We often feel insignificant, like dust motes floating in a hostile void. But in this view, our universe is a mother. Its purpose, if it can be said to have one, is to foster the conditions for these births. The galaxies are the ovaries of the cosmos. The stars are the eggs. And gravity is the force of fertilization. There is a fascinating philosophical implication here regarding technology. A few years ago, when the Large Hadron Collider (LHC) was being switched on in Switzerland, there was a ripple of panic in the media. People feared that smashing particles together at such high speeds might create a microscopic black hole that would swallow the Earth. Physicists assured us that this wouldn't happen, that even if a tiny black hole formed, it would evaporate instantly due to Hawking radiation. And they were right. The Earth is still here. But think about the concept. If a civilization becomes advanced enough, if they build a machine powerful enough to concentrate energy into a tiny point, they might be able to create a black hole artificially. In the logic of our theory, this means that an advanced civilization has the power to create a universe. Perhaps this is the ultimate act of creation. A physicist in a lab presses a button. A particle collider hums. A tiny point of darkness appears for a nanosecond and vanishes. To the physicist, it was a fleeting experiment. But on the inside of that pinprick, a big bang occurred. A timeline began. Stars formed. Galaxies spiraled. And perhaps billions of years later in that timeline, a creature on a planet looked up and wondered where its universe came from. It came from a machine in Geneva, or a lab in Andromeda. This is the concept of laboratory universes. It suggests that intelligence itself might be part of the reproductive cycle of the cosmos. Maybe nature makes black holes through collapsing stars, but intelligence makes them through science. We are not just observers. We are participants in the proliferation of reality. But let's return to the natural seeds. Primordial black holes are currently a leading candidate for one of the biggest mysteries in astronomy: dark matter. We know there is extra gravity holding our galaxies together. We can't see it, but we feel it. For a long time, we thought it was some exotic particle, but we haven't found that particle. What if dark matter is just billions of tiny black holes swarming around the galaxies? What if the invisible mass holding the Milky Way together is actually a swarm of baby universes? It is a poetic thought. Our galaxy is held together by the weight of the worlds it carries. We are orbiting a cloud of potential realities. However, there is a catch. If black holes are universes, what happens to the stuff that falls in? If I throw a chair into a black hole, does that chair appear in the baby universe? Not exactly. The matter is crushed, broken down into energy and fundamental information. The baby universe receives the mass and the charge and the spin, but it doesn't get the chair. The furniture doesn't survive the transition, but the information does. As we discussed with the holographic principle, the data is stored on the horizon. This means the baby universe inherits the genetic code of the parent, even if it doesn't inherit the furniture. This inheritance is what Smolin called the cosmological natural selection. But it relies on the idea that the inside of a black hole is a stable place, a place where geometry can expand. But not all physicists agree on what the inside looks like. Some theories, born from the strange world of string theory, suggest that there is no inside at all. They suggest that the black hole is not a hole, but a ball of string, a fuzzball. And if the fuzzball theory is right, it challenges the whole idea of living inside. Or perhaps it just changes the texture of the walls. To understand if our universe is a smooth bubble or a tangled knot, we have to zoom in to the smallest scales imaginable. We have to enter the vibrating world of string theory. The deeper we look into reality, the fuzzier it gets. In our everyday world, objects have hard edges. A table ends where the air begins. But in the world of quantum mechanics, edges dissolve. Particles are not little billiard balls. They are waves of probability. They are here and there at the same time until you look at them. For decades, the standard picture of a black hole was simple. It had the event horizon, the smooth, immaterial point of no return, and the singularity, the infinite dot at the center. Between them was empty space, a vacuum where you would simply fall until you were torn apart. But this picture causes a massive headache for quantum mechanics. It is called the information paradox. If information falls into the black hole and the black hole eventually evaporates, where did the information go? You cannot destroy information. It violates the rules of the quantum universe. String theory offered a radical solution. String theory posits that the fundamental constituents of the universe are not point-like particles, but tiny, one-dimensional vibrating strings. Like the strings on a violin, they vibrate at different frequencies. A string vibrating one way looks like an electron. Vibrating another way, it looks like a photon. Everything is music. When string theorist Samir Mather looked at black holes through the lens of strings, he found something shocking. The math didn't show a singularity, and it didn't show empty space behind a horizon. Instead, the math showed that when you pack enough strings together, like the mass of a collapsing star, they don't crunch down to a point. They tangle. They form a massive, fluff-filled ball of vibrating strings. He called it a fuzzball. In the fuzzball hypothesis, a black hole is not a hole. It is a physical object. It is like a planet made of strings. The event horizon is not a spooky, empty boundary. It is the surface of the fuzzball. It is where the atmosphere of the star ends and the tangled mess of strings begins. If you fell onto a fuzzball, you wouldn't pass through a horizon and float in darkness. You would hit the surface. You would be absorbed into the tangle. Your strings would join the cosmic yarn. Now, how does this fit with our universe inside a black hole story? At first glance, it seems to kill it. If there is no empty space inside, just a knot of strings, how can galaxies and stars and people exist in there? We are not living in a ball of yarn. We see empty space. We see vacuum. But wait. String theory is a theory of extra dimensions. It requires 10 or 11 dimensions to work. We only see 3 spatial dimensions and 1 time dimension. The other 6 are curled up, hidden from us. What if the fuzz inside the fuzzball is just how the higher dimensions look from the outside? To an observer outside the black hole, the interior looks like a chaotic, high-entropy ball of strings. It looks fuzzy, but that might be a matter of perspective. Think of a hologram again. If you look at the holographic plate itself, it looks like a chaotic pattern of swirls and interference lines. It looks like a fuzz. It makes no sense. But if you shine a laser through it, if you view it from the correct perspective, that fuzz resolves into a perfect, clear, three-dimensional image. Perhaps we are living inside the fuzzball, and from our perspective, the strings have resolved into smooth spacetime. The chaotic vibrations of the strings on the surface of the fuzzball, the horizon, might be projecting the reality we experience. The tangle is the code. The universe we see is the user interface. This resolves the singularity problem in a new way. There is no infinite density because the strings have size. They cannot be crushed to zero. They just pack tighter and tighter until they become a new state of matter. Our Big Bang might have been the phase transition, the moment the fuzzball formed and the strings locked into a new configuration, creating the illusion of 3D space for the internal observer. This also saves the information. In the standard black hole model, the information is lost in the singularity. In the fuzzball model, the information is distributed throughout the ball. It is in the strings. If the fuzzball evaporates, the information leaks out in the radiation, imprinted on the departing strings. The book you threw in isn't destroyed. It is just translated into a new language of vibration. If this hypothesis is true, it makes the universe feel much more tactile. We are not floating in nothingness. We are floating in a substance. Space-time is a material. It can be woven, knotted, and frayed. And it brings us back to the idea of the membrane. In string theory, our entire universe might be a brain, a multidimensional sheet floating in a higher dimensional bulk. The event horizon of the black hole is the edge of our brain. The fuzzball theory creates a bridge between the cold geometry of Einstein and the vibrant uncertainty of quantum mechanics. It suggests that the monster in the dark is actually a maker. It is a loom that weaves reality out of chaos. But if the universe is a fuzzball or a bubble or a projection, one question remains naggingly unanswered. If there are so many universes, billions of baby universes, an infinite chain of nesting dolls, and if life is a natural byproduct of this black hole manufacturing process, then where is everyone? Why is the sky silent? We have looked for radio signals. We have looked for laser pulses. We have looked for Dyson spheres. We have found nothing. Could it be that the very structure of the black hole universe is the reason for the silence? Could the event horizon be the ultimate quarantine? We call this the Great Filter. But in this cosmology, the filter isn't biological. It is geometrical. We are trapped in our own private room, and the walls are too thick to shout through. We have spent this night exploring the architecture of reality, building a model where universes are nested inside one another like Russian dolls, born from the collapse of stars. It is a loud, crowded, and fertile picture of the cosmos. It suggests that universes are common, that black holes are factories, and that the laws of physics favor life because life is the byproduct of a system designed to reproduce. But if the cosmos is so fertile, if there are so many rolls of the dice, we run headlong into the silence. The Fermi paradox. Where is everyone? If our universe is 13.8 billion years old, and if there are billions of planets in our galaxy alone, statistics suggest we should have been visited by now. Or at least we should hear their radio leakage. We should see their megastructures blocking the light of stars. But we see only wilderness. The standard explanations for this silence are grim. They talk about nuclear war, about resource collapse, about biological filters that wipe out life before it can leave its planet. They suggest that intelligence is a self-correcting mistake, destined to destroy itself. But the black hole universe hypothesis offers a different, stranger, and perhaps more hopeful explanation. It suggests that the silence isn't caused by death. It is caused by geometry. Think about the structure we have described. A black hole is a one-way door. You can fall in, but you can't get out. This means that if there are civilizations in the parent universe above us, they can never visit us. They can never send us a message. They are separated from us by an event horizon that is absolute. To them, we are just a heavy, dark sphere floating in space. To us, they are a memory from before the Big Bang. The same logic applies downward. If our universe contains billions of baby universes inside its own black holes, and if any of those universes have life, they can never contact us. They are sealed in their own spacetimes. They could be thriving, building galactic empires, singing songs and broadcasting signals, but none of it can cross the horizon back to us. We are living in a multiverse of solitary confinement. Every universe is a quarantine cell, cut off from its neighbors by the laws of gravity. But what about this universe? What about the aliens that might exist in the Milky Way, right here alongside us? Why haven't they said hello? This brings us to the concept of inward expansion. Humanity is currently obsessed with outward expansion. We want to go to Mars. We want to go to Alpha Centauri. We imagine a future where we colonize the galaxy, hopping from star to star in tin cans, terraforming planets over thousands of years. It is the logic of the explorer. We want to conquer distance. But distance is hard. The speed of light is a cruel limit. Interstellar travel is slow, expensive, and dangerous. Now, imagine a civilization 1,000,000 years older than us. They understand the physics we are just beginning to guess at. They know that the universe is a nesting doll system. They know that black holes contain new, fresh realities. Why would they spend thousands of years traveling to a dead rock around another star when they could build a machine, a particle collider, a gravimetric lens, that creates a black hole right there in their own solar system? If they create a black hole, they create a new universe. A universe where they can perhaps tune the laws of physics. A universe with fresh resources, untouched by entropy. A universe they can design. Perhaps the ultimate destiny of a high-level civilization is not to conquer the galaxy, but to leave it. not by dying but by migrating, by slipping through a self-made event horizon into a pocket reality of their own making. This would explain the silence. Advanced civilizations don't expand. They transcend. They turn inward. They don't build empires of noise. They build doors of silence. If this is true, then the great filter is not a barrier that kills you. It is a test of physics. Once you understand the nature of the cosmos, you realize that the real frontier isn't out there among the distant stars. It is down there. In the high-density singularity of a new beginning, we look for them with radio telescopes, expecting them to be shouting across the void. But they might have already left the room, closing the door behind them. This perspective shifts the feeling of cosmic loneliness. We aren't alone because others have died. We are alone because the others have grown up and moved into their own apartments. And it forces us to look at our own black holes differently. We see them as dangerous, radiation-spewing monsters. But maybe they are the homes of those who came before. Maybe the supermassive black hole at the center of the Milky Way, Sagittarius A*, is not a natural formation. Maybe it is the residue of a billion-year-old civilization that packed its bags and created a new world, leaving behind only a gravitational footprint. It is a wild speculation, of course. We have no proof, but in a universe this strange, the line between physics and philosophy blurs. There is one final implication of this isolation. If universes are cut off from one another, it means that every universe is a precious, fragile experiment. We cannot call for help. We cannot import resources from the parent universe. We have to make this one work. We are the stewards of this specific bubble of spacetime. We are the consciousness of this specific black hole. And if we fail, if we destroy ourselves or our planet, this specific experiment ends. The multiverse will carry on, the chain of nesting dolls will continue elsewhere, but our unique story, our unique variation of the theme will be lost. The silence of the sky is a reminder of our responsibility. There is no one coming to save us. There is no federation of stars waiting to admit us. We are, for all practical purposes, alone in the dark. But we are not unprotected. We are held in the embrace of a horizon that shields us from the chaos of the higher dimensions. We are safe in our shell, and we have 13.8 billion years of starlight to keep us company. As we reach the end of this journey, we have to ask ourselves, how does it feel to know you might be living in a black hole? Does it make you feel trapped, or does it make you feel held? We started this journey with a question that sounded like a nightmare. Are we living inside a black hole? The image it conjured was one of crushing darkness, of being trapped in the belly of a beast. But as we have walked through the physics, the geometry, and the philosophy, the image has changed. The beast has become a mother. The darkness has become a womb. The trap has become a cocoon. We have seen that the mathematical coincidences of our universe, its size, its density, its expansion, align perfectly with the interior of a black hole. We have seen how the Big Bang could be the big bounce of a collapsing star from a higher dimension. We have seen how the rotation of that parent star could be the invisible axis that aligns our sky. We have explored the idea that our reality is a hologram projected from the horizon, and that the confusing force of dark energy might just be the growth of our container as it feeds in a universe we will never see. We have touched on the idea that universes reproduce, evolving through natural selection to become better at making stars, better at making black holes, and consequently better at making us. And we have faced the silence, realizing that the isolation of the event horizon might be the reason we seem alone, a cosmic quarantine that allows each universe to develop in peace. When you put all these pieces together, the feeling is no longer vertigo. It is belonging. For so long, humanity has looked for its place in the cosmos. We felt like accidents. We felt like lonely wanderers on a small rock in an indifferent void. We worried that the universe was cold and dead, and that we were the only sparks of warmth. But the black hole universe theory tells a different story. It tells us that the universe is a living system. It breathes, it grows, it reproduces, it has ancestors, and it has offspring. We are not accidents. We are the inevitable result of a physics optimized for life. We are the way the universe knows itself. We are made of stardust, yes. But that stardust was forged in the collapse of a previous reality. The atoms in your hand have a lineage that stretches back through the event horizons of countless universes, layer upon layer, deep into the infinite past. You are not small. You are part of an infinite chain. And think about the protection. If we are inside a black hole, we are shielded. Whatever chaos exists in the parent universe, supernovae, radiation storms, entropy, cannot touch us. The event horizon is the ultimate shield. We are drifting in a safe harbor, allowed to evolve, to learn, to love, and to dream, protected by the gravity of a star that died to give us life. That it gives a new meaning to the night sky. When you look up tonight, don't just see empty space. See the interior of a vast, expanding shell. See the darkness not as an absence of light, but as the walls of our home. And realize that we are also creators. Every time we study the stars, every time we understand a little more about gravity, every time we push the boundaries of science, we are participating in the cycle. We are the mind of the black hole waking up. Perhaps one day, millions of years from now, our descendants will understand the physics well enough to create their own horizons. They will become the parents of new realities, passing the torch of existence down into the depths of the fractal. But for now, it is enough to just be here, to breathe in the atmosphere of this specific, beautiful, fragile bubble, to appreciate the Goldilocks laws that let us exist, to marvel at the illusion of the stars. The universe is a mystery, layered and deep. We may never know for sure if we are inside a black hole. We may never see the parent universe. We may never hear the siblings in the dark matter. But the possibility alone changes us. It reminds us that reality is stranger and more wonderful than we can imagine. It reminds us that even in the dark, there is structure, there is purpose, there is a story, and you are writing that story right now just by being alive. Thank you for wandering through this hypothesis with me tonight. The universe is vast, and the questions are endless. But that just means we have more to explore together. If you enjoyed this journey into the depths of cosmology, and if you find comfort in the strange questions of existence, please consider liking this video and subscribing to the channel. It helps this little space of curiosity grow, one listener at a time. Sleep well, dream deep, and remember, even in a black hole, there is light. Good night.